Hi guys, how are you? I hope you're doing great and that you are very healthy. And well, this is the new way how we're gonna have lessons. Welcome to my house. I guess it's never too late to become a YouTuber. Just hope to not go too viral. And well, let's start having a look to what we saw in previous lessons. Remember that the second lesson we had, I told you that light has four properties: reflection, refraction, interference, and diffraction. The first two that we already know very well are studied in an area that is called ray optics or geometric optics, because we use a lot of geometry for that, and also because we consider the light travels as a straight ray. it it's also sometimes called like the particle approximation, because these two properties can also be studied considering light as a particle. Remember that in the time of Newton there were people that had a theory that light behaves as a particle, including Newton, and other people that had the theory that light is a wave that behaves as a wave. So, well, reflection and refraction, they're very easy to see in nature. You've been sending different pictures about demonstrations you did in your houses. You know very well what is reflection. When light reflects in the boundary of a medium. And as you see, well, I draw a little ball here because we can consider again light as a particle. If you drop a ball to the floor, it's gonna have the same reaction. The same as refraction. Remember that Newton divided the white color into the seven different colors using a Newton prism and considering light as a particle. But the thing is, for today's lesson, how can we prove that light is a wave? How can we prove that light behaves as a wave? So, well, there was a man, again from England, in the early 800s that made an experiment. His name was Thomas Young, and let's have a look to what he did. Look where I am in our classroom, but it's empty. Feels so lonely without you guys. Well, I'm here just to show you what Thomas Young did to prove that light behaves as a wave. To do that, I have a laser, just a normal pointer. I have a whiteboard here that we're gonna call screen because we're gonna project the laser over there. And between these two things, I have these kind of little windows that are actually gratings, diffraction gratings. And the first one in the left has 100 lines per millimeter, the second one 300 lines per millimeter, and the third one 600 lines per millimeter. So imagine this is the little window and it's divided with all these lines. Okay? So the question is, what's gonna happen if we pass a ray of laser through these gratings? What are we gonna see in the screen? Take a moment to think and to imagine what could happen. 1 minute, 3 hours, 60 days. So if light behaves as a particle, what I imagine that could happen is that imagine that this is the laser going through the grating. What's gonna happen? What are we gonna see here in the screen? Well, maybe the same dot, but divided. Then I see maybe the grading over there with empty spaces. So let's see what's gonna happen. I'm gonna turn off the light. Wow. So, first of all, there's not just one dot. There's many. One, two, three, four, five. Maybe more. Yeah, there's one more over there. What else we see? Well, this one in the middle is clearly more intense than the other ones. Actually, the intensity goes down to the right and to the left too. And look, if I move the laser, the distance of the laser, it doesn't really affect the distance between the dots. They move a little because my pulse is not the best. But what happens if I change the distance between these two? Well, yeah, the distance between the dots change. Smaller, larger. What happens if I move to 100 lines per millimeter? There's even more dots. And 600 lines, just 3 dots. So how can this happen? Well, we're gonna talk about that in today's lesson. And one other thing, I also have this very common tool. I'm gonna measure the distance between the screen and the grating, and also the distance between the dots for each one of the gratings. And by the end of the lesson, you will be able to calculate the wavelength of this laser, of this light, just with that 3 measurements. Okay, so let's go for it. So to have a look start to understand what happens over there in the classroom, let's have a look to these two concepts: interference and diffraction. So interference is basically when two waves overlap and form a third wave. So if these two superpose, there's gonna be a resultant wave. Okay. And well, we can have two kinds of interference: constructive and destructive interference. Constructive is when the two waves that overlap are basically in the same position. The crest and the throat are in the same position, so they're gonna zoom each other. Then it's gonna increase the double in other ways. Okay. And the destructive interference is when one wave it has in the position of one wave is the crest, and in the other one is the trough, so they're gonna cancel each other. So just have a look here. If here we have y and x, and here we have one wave that goes this way, and the other one goes in the others. So what's gonna happen? Imagine that here the maximum value here is 10, and the minimum value in the other one is minus 10. So if they overlap, 10 plus minus 10 is 0. And the same with all the points. They're gonna have a sum of 0. And that's how they cancel each other. And well, what's diffraction? Diffraction is the change of direction and intensity of waves after passing by an obstacle or through an aperture. So imagine that you are in the ocean or in a lake, and these things here are the waves. But imagine that you have a wall right at the shore, but with a little aperture over there. So this is what would happen with water. The waves are gonna hit this barrier, and in this little aperture there we're gonna have this kind of waves. Okay, something similar happened with sound. So how sound travels, let's imagine that here you are in your room here, and that you have your speaker that is it's playing music over there. So the sound is gonna travel like this, and at this point it's gonna form again this kind, but of course with less intensity, and that's how the music will reach your ears. So that's basically diffraction. Okay, it's these waves passing through a small aperture. Self-check the fact that you can hear a person or a speaker behind an open door even when you don't see the person or the speaker. It's a result of sound waves diffraction. Okay, great. We already know what is interference and what is diffraction. If we can prove that light has interference and diffraction, we will prove that light is a wave. But first, to observe interference, we need some conditions. And that's it, that between two sources of light, they must be coherent. We want that two sources of light have interference with each other. And yeah, we need that they have to be coherent. And what does that mean? That they must maintain a constant phase with respect to each other. Oh my god, what is coherent, what is phase, what this it means. Let's have a look to these concepts. Phase difference is the difference expressed in degrees or time between two waves having the same frequency and reference to the same point in time. In other words, if we have again two waves, we say that they are in phase when they reach the maximum point. Let's imagine that this is a perfect draw, please. And well, we say that they are in phase when they reach the maximum value at the same time. Okay? If they have the same frequency, they're gonna be in phase all the time because they're gonna reach the maximum value all the time at the same at the same time. And if there's a difference, imagine that this wave it's a little more to the right, they're gonna reach the maximum values in different times. So that's what is called the phase difference. For example, here we have two waves that they have a phase difference because they are not reaching the maximum point at the same time. Actually, when one is reaching the maximum point, the other one is reaching the minimum point. So what would happen if they have interference? They would cancel each other. It would be a destructive interference. And what's the phase difference here? It's one half of a time period. Why one half of a time period? If you look here, this is the wavelength, and the difference between these two, it's actually half wavelength between the wavelength is the other crest from the other wave, and that's the phase difference. Here you have a little challenge. If you want to have a look afterwards, it comes with an answer, so don't worry. Try to think what's the phase difference between these two waves. And well, the other concept was coherent waves. What is a coherent wave? By coherent, it means that we have waves with equal frequencies and wavelengths, and that they are in phase or have a definite phase relationship. They have constant phase. Okay, that means that we have same practically same kind of waves, that the relation between them, it will not change in time. Okay, if we have this, that they're not, the relation between the, imagine that they're not reaching this at the same time, the maximum point, but that they will always do it in the same point here. Okay, it's gonna be constant, that phase difference. So when we have that, we have a coherent waves, and that's actually the basic concept to have laser lights. The laser I was using before in the demonstration is a coherent light because all the waves have the same relation. They have constant difference, but they have same frequencies and wavelengths. And if their phase is not the same, at least it's the same difference all the time. Not like other kind of lights that, as you can see here, it's a mix of different kind of wavelengths and different kind of phases. So to have interference, we need that. We need uh, we we need wavelengths that are constant in terms of phase difference, and that they have the same frequencies or wavelengths. That's for what we wanna do with that. Well, we're gonna do what I did in the classroom. Look what is happening here. In this picture, you have a grating again. In the case of the experiment I did in the classroom, the grating, it was three different kind of gratings. One was like 100 lines per millimeter, the other one was 300, and the other one 600 lines per millimeter. So a lot of little spaces. Okay, here we have just two, not 10 per millimeter, not 100 per millimeter or 800 or 600 per millimeter, but just two. Okay, sorry. Let's imagine that here, as in the example I show you, I told you with the waves in the ocean, we have light that is coming this way. Okay. In this case, these lines here represent the crest of the wavelength of the wave, sorry. You're gonna say, wait a minute, this it doesn't look like a wave. A wave, I was drawing a wave like that all the time. So well, imagine that we see these kind of waves like this here when we see that in the ocean, where we have the water until the half of our eyes practically. Okay, now we are watching the waves from above. Okay, and the waves, we are seeing these waves in two dimensions now. Okay, so practically, well, this is actually these are called wavefronts, and lambda, the wavelength, is gonna be the difference between these two lines. So practically these straight lines, solid lines here, are the crest, the maximum values of the wavelength, and this dotted line here, it's the trough of the wavelength. Okay, so we need to visualize the waves in this way to understand this concept. So what's gonna happen when they reach these two little spaces here? They gonna diffract. Again, they come here and they start to do this, like the sound in the rooms that we were saying. Okay, and again, the difference between these two lines, this one and this one, is lambda, the wavelength. So what are we gonna have at the end? We're gonna have something like this. So what's gonna happen here? This is the representation of these two. Okay, so there's gonna be different waves that are gonna interfere each other, and they will have constructive interference and destructive interference. So in the screen, we're gonna see some parts that have light, like the dots we saw it in the experiment I did, and some dark spaces. Wherever there's light is because we had a constructive interference here, and wherever there's darkness, it's because there was a destructive interference here. Okay. And again, we're talking about interference, so that means that the waves here are coherent. How Thomas Young get to that? Well, he used the same source of light. Instead of using two, he used one, and he used the double slit. These two operators here is for that. So then we can use just one source of light that it's divided, and then we will not have problems with coherence and phase. So that was very smart from Thomas Young. So there's a video that I need you to watch where you will have a very good explanation. It's not a long video. Take your time to watch it. And you will have a very good explanation of how we have this interference, constructive and destructive, to have these dots here. So why the experiment of double slit by Thomas Young, it was so important? Because he proved that light can have interference and diffraction. Then he proved that light is a wave. So what I was telling you before, when we have imagine that this is the double slit, and that again we are drawing the waves this way. Okay, so again we are here. Whenever there's dark places here, it's because of destructive interference. Okay, and whenever there's uh, light or color, it's because it's a constructive interference. Okay, look here. So we can relate the position where we're gonna have these dots here. Imagine that the dots are here, 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 all over here. So we can relate these 2 points with also the middle. And also the distance between the points and the distance between the screen and the grid. We can relate all of that, and at the end we will have a equation. You're gonna see the explanation very good also in that video. And that equation is this one here. Where d is the distance between the two little apertures, the little d, then we're gonna have, well, we're gonna see it later, but well, we're gonna have the angle that is practically the, if we draw a right triangle between the aperture and the, let's say the point of light we have in the screen, if we draw a right triangle, we gonna have an angle over there, okay, which is this one here. And we're gonna have the wavelength, which is great. Now we're gonna be able to measure the wavelength just knowing this distance and the angle. What is m? So m, as we saw it in the experiment, we have all different kind of dots here, and m, it's the number of dots that are in relation with the one in the middle. In other words, this is m1 and this is m2. This is m minus 1 and this is m minus 2. Just that, natural numbers. There's another value that is important for us to be aware, that is the distance that I was telling you about before, the distance between the grating and the screen, which is called D, but capital D. And I was telling you about this angle here. To find this angle, we just need to know that capital D and the distance between the two dots. So that's it. If we measure the distance between the two dots, the distance between the screen and the grid, and if we know the distance between these two apertures here, we can find lambda. Of course, we're gonna know the value of m depending of uh, which value of y we we're gonna use. If this is the first point or if it's the second, we will have to use this y, and of course then we will have to divide it by m, and this m is gonna be 2. Okay, is it clear? So well, you will have to measure to calculate lambda, as I was telling you, with that values. Here we have the values of the diffraction grading. The gradient was, sorry, this is 100 lines per millimeter. And also here. This is the distance. This is the distance between the screen and the screen and the grade. Here is the grade. That's 30 centimeters. And the distance between the points that I show you here. These are that values, okay, in centimeters, everything. So I was telling you that, well, Thomas Young used just these two little slits. Why we used a grid? Well, when we use a grid instead of just two slits, we have these very nice points with very clear distance between them. If we use just two slits like Thomas Young, we have this, which is not too clear where where a point ends and where it starts another one. Okay, that's why, well, we're using that, and that's the only difference. There's some theory behind that. If you want to know why using these kind of grids we have these points, just ask me and I will send you good information about why this happens. Okay, so this is the grid we used for the experiment. What happens if we have just one single slit? Depending on what's the size of that little aperture, we're gonna visualize different kind of diffraction in the screen. Okay, again, if we imagine light as a particle and we send light through this little aperture here, we will expect to see just that little part in the screen, a line that is vertical. But what happens? It's actually a horizontal line because light is a wave. So look, red color, red light, it has this lambda, this wavelength. So when you go to calculate the wavelength with this equation and these numbers here, we were using red color. So the wavelength, it should be around this number. Let me know. Okay. Of course, I don't have a perfect eye. My my measurements of the distance are it's not perfect. So let me know more or less how which values you get at the end. Okay. And as I was telling you in the video also about the demonstration, the dot in the middle, it's always the more intense, and to the right and to the left, it lose that intensity. So if we make a graphic of the intensity, it would be something like that. Look here. So that's why when I did the experiment, the dot in the center had more intensity than the others. Okay. And well, that's it about interference and diffraction. We proved that light behaves as a wave during all the lesson. For your homework, you have to fill a Google form. You have to read about the film interference. Just with these three last slides, it's enough. You're gonna see that these beautiful rainbow colors that we see in the bubbles or in the oil are not really rainbows because they're not created by dispersion of light but by interference, same as CDs. They're not rainbows because it's not dispersion, is interference. Okay. And when you go, you also have as a homework to find the wavelength of the light I used here. You have to use again this equation. You have to find the angle using this equation here. Okay. And well, you know everything. You're gonna ask me, what is D here? In these numbers, where is D? D is the distance between the two apertures here. So in this grading that I use, it's gonna be the difference between the many apertures that there's in that grading. So that's that aperture, the distance between those apertures, it's gonna be, in this case, for example, 1 divided by 1 by 100. Okay. And the magnitude, the unit, sorry, is gonna be millimeters. Okay, be careful with units. You have centimeters here, you have millimeters, and normally wavelengths, if you're talking about colors, are in nanometers. Okay, so try to have the answer in nanometers. Between these three, you will use the equation for each one of these gradings, and you should have the same answer for the three different gradings. Okay, more or less. It's gonna depend on how I measured these things here. If you do the good calculations, but it shouldn't be too different. It shouldn't have a difference of 100 nanometers. Okay, so have a look to that, and let's see what you find. That's gonna be your homework. I'm gonna place it also as an assignment in Google Classroom. So thank you very much. I hope it was useful. I'm sure I'm gonna have more experience doing videos with the time. And I miss you guys. I miss you in real life. Bye.